Hi everyone. In this video I'll be going over section 11.5, solving systems of nonlinear equations. So way back when we were solving systems of linear equations. So if this non prefix weren't there, this would be no different. So the only difference is this first part of this word. So we're going to be able to solve systems of like two circles or an ellipse in a circle or a straight line and a hyperbola. Okay, so all these conic sections that we've been seeing are nonlinear. But before we get to an actual nonlinear case, I wanted to just remind us of what we had been doing. So these are actually two lines. So this is not necessarily 11.5 material, but this is stuff from earlier. So let's see. Let's try to solve this by substitution first, and then I'll go on and talk about addition, and then I'll go on and talk about graphing. Okay, so by substitution, what is meant is you can solve for one of the variables. So maybe I'll subtract 2x here from the second one. And then we would have y equals -2 minus 2x. And then what you can do with that is substitute it into the other equation and replace y with it since it's equal to y. So we can write 2x plus 3 times -2 minus 2x. And this all still equals 6. So distributing, so 2x plus, this will turn into -6 actually. So I'll just say -6. And then 3 times the -2x, this is -6x, equals 6. So 2x minus 6x is -4x. And then I can add this 6 over also. So it looks like we have -4x equals 12 at this stage. Divide by -4 finally. So x equals -3. So that's the x location apparently at which these two lines intersect. And to find the y component, what I'm going to do is just plug this x in right here. So y equals -2 minus 2 times -3. In other words, -2 plus 6, this is 4. So apparently we expect an intersection at -3, 4. And this would be our solution in that case. And that's solving this using the substitution method. So what about the addition method? We saw some of this a while back too. I'll write down this system again. So the elimination method was also something we called this. So addition/elimination method. So what we want to do is add these together with the hopes of eliminating one of our unknowns. If I add together now, nothing will get eliminated, right? We'll just have 4x and 4y and 4. So nothing will kind of simplify. So what we want to do is actually multiply by a non-zero number and then do the adding portion. So what I'm going to do is choose to multiply, well, maybe I'll just write it over here. I'm going to multiply this one by -1. So that will lead to -2x minus 3y. So I'm multiplying this -1 in. And then this would equal -6. And then I still have the other equation. I'll write that down. Now when we add these, we do get an elimination to occur, right? The -2x plus 2x, that just goes away. -3y plus y is -2y. And this would equal now -8. Solve for y. So y would equal 4. What you can do is then go back and eliminate then eliminate y's, so you can solve for x. So maybe I'll just write this down again, this original system. So keep in mind, this is for lines that I'm doing this, but these same techniques, the substitution technique and the addition technique that we're learning, or we're refreshing, is applicable to the nonlinear case. Okay, so the same techniques that we're using here for the lines, you're going to be using for the nonlinear cases. So to eliminate the y's, well, I have a 3 above, I have a 1 below, so I'll multiply this one by -3. So we now have, I'll just write that first one again. And then distribute the -3, we have -6x minus 3y equals 6. And then add. So -4x. And then these do cancel. We'll get at that elimination over here on the y's this time. And then this equals 12. Divide by -4. So x equals -3. So we got y equals 4 over here, x equals -3. In other words, we have this as our solution. Point being, it's the same solution, right? Same solution as we got before, just a different method. And then what I was asking us to do is to then solve this system a third way, and to do that by graphing. So let's see that. Maybe I'll do that in a different color. So that first equation here, if I get this into slope-intercept form, I could subtract this 2x. So that first one can be written as 3y equals -2x plus 6. Then divide by 3. So we get y equals -2/3 x plus 2, right? Just from this simplification. So here's my y-intercept, here's my slope. So from 0, 2, I'm going to count down 2 and to the right 3. So here's my y-intercept, there's that 2. From there, I'm going to go down 2 because of the -2, and then to the right 3. Looking for something that I can use as a straight edge. Okay, here's a book. Not the greatest thing to use. This thing works. Sorry about this. So I just need this line to be kind of straight so that we can see what the solution might be. All right. So there's that one. And then the other one, So here, I actually have this in slope-intercept form right there. So I can go ahead and graph this one. We have a y-intercept of -2, right? This would be the same as y equals -2x minus 2. So we have a y-intercept of -2 now, and a slope of -2. So I go down here to -2. This graph is weird. This is actually -1, -2. And then I go down to and over 1. Sorry, what I did was I went down to and over 1 because of this -2/1 slope. And you can do that again if you need from this new point, go down 2 over 1. Okay, and then I'll just make my best line I can through there. Okay. Keep in mind, graphically, that solutions are intersections. If there is an intersection, right? We don't need to intersect, but these do. And it looks like that point would be -3, 4. Right? Same as the solutions we got from substitution and by addition. Keep in mind you can check your work. Oops. So you can check your work by plugging in these answers always. So I'm not going to do it right now, but I could take these numbers and plug them in for x and y, make sure I get a 6 on the left, make sure I get a -2 on the left. Let's try an actual nonlinear case. All right, so as I was saying, the ideas we were just using on the linear cases can be extended to these nonlinear cases. So we have, it says, solve using the substitution method. All right, so I'm seeing we have some quadratic. So this would be actually a parabola. And then we actually do have a line here. So we may have a situation like, and I'm just sketching something, this is not exactly it, but we may have a situation like this, where we have a parabola, and then we have this straight line, perhaps coming through it, like this, okay? So this is just a sketch of a possible orientation of this parabola and this line. It could be, though, that we have this parabola and this line, right? It could be that this parabola is there, but then the line just misses it. And in that case, we would have 0 solutions. So we could have 0 solutions. We could have 2 solutions. We could have 1 solution, right? So there's the possibilities. So by substitution, basically what I'm going to do is I'm going to isolate one of the variables, and I'm just going to choose to isolate this y right here. Sorry, this y right here. So I'm going to add 1 to both sides. So x squared plus 1 equals y. And just as before, what I can do is now take this thing and plug it in for y right there. So 4x, right, that's still there, minus, so I need to subtract all of this thing, so the parentheses are crucial. So x squared plus 1 equals -1. Now I'm going to solve this. So distribute the negative, so 4x minus x squared minus 1 equals -1. Go ahead and add 1. So 4x minus x squared equals 0. So I'm noticing we can factor. So we'll factor out an x, leaving behind a 4 minus x. So x must be 0. This is a 0 product property now. Or 4 minus x needs to be 0. So x is 0 is apparently a solution. And if I add x here, we get 4 equals x. So we have like an x1, I'll just call that 0. And we have like an x2, I'll call that 4, from this work down here. Okay, so what we now do is I'm going to take x1 and I'm going to plug it in for x, and that's going to spit out a y1. So let's do that. So 0 squared plus 1 equals, this is y1, right? I'm just labeling it so I kind of connect these two. I don't want to accidentally think that this 4 led to this number. So y1 is 1. So one of our intersection points, I'll just write it down here, is x equals 0 and y equals 1. So this apparently is going to be one of our solutions. We had another x, so x2 is 4. So plug that in now. So 4 squared plus 1 equals, this is y2. Since I'm plugging in x2, it's corresponding to y2. So 16 plus 1, 17 is y2. So I would have another solution down here as x was 4, and this is just a comma, by the way. And then we got a y of 17. You can always check these. All right, so let's just go ahead and do that on this one. So let's check 0, 1. So on the left, I don't know if I need the calculator for this one. I plug in a 0 for x. I get a 0. I plug in a 1 for y. I get 1 minus 1, so I do get 0 equals 0. So this one does work for the first one. For the second one, plug in a 0 for x. I get 0 here. Plug in a 1 for y. I get negative 1 equals negative 1. So this one works in both. Let's check this one. I'll go ahead and use the calculator here. So 4 squared, that's 16. So I have 16 on the left. Plug in the 17, right? For y, I get 17 minus 1, so 16 does equal 16. I actually don't need the calculator there either. Plug in now into the second equation, the x. So 4 times 4, right? Actually plugging in and using the calculator now. Minus 17, this should be negative 1. So yeah, both these work. Let's try another one. Okay, so it says solve using the substitution method, graph to check your answer. All right. So I'm noticing that x is fairly alone. I just need to subtract over this 2y. Keep hitting the camera. So we get x equals negative 2y. And what we're going to do now is, just as before, since we're using substitution, we're going to take this and substitute it in for x. So negative 2y minus 1 squared plus y minus 1 squared equals 5. So now we have one equation with only one unknown, right? Y. So I need to expand. So I'll do some quick foiling. I would get positive 4y squared. We would get positive 2, but then I would have 2 of those. So I'll have plus 4y. You can check my foiling on that. And then lastly, we'll have a positive 1. Over here, foiling quickly again, I'll have a y squared, a minus 2y, and then a plus 1. Now we're combining like terms and solving this quadratic in terms of y. So 4y squared, that's 5y squared. 4y minus 2y, that's 2y. 1 plus 1 is 2, and then I'll subtract over the 5 at the same time. So we would have a 2 and then a minus 5, so a negative 3, and this would all equal 0 now. All right. We can use the factoring technique or the quadratic formula. I'll just use the quadratic formula with a equals 5, b equals 2, and c equals negative 3. So y would equal opposite of b, plus and minus the square root of b squared minus 4 times a times c, all over 2 times 5. So here's the plus case, 3/5. And then change this plus to a minus. Negative 1, so y minus is negative 1. Okay, so we have 2 y's. What I'm now going to do is plug those y's back into this to get the x's. So x plus will come from plugging in y plus. So I'm just using pluses this time to denote the difference between the results. I used a 1 and a 2 earlier. So whatever you choose, it's totally fine. You just don't want to get these things crossed up, right? Like, just for instance, I could have accidentally said 0.17 and 4.1. You know, you could get the points mixed up, and you just want to keep track. So x plus would be negative 2, right? I'm going into here with y plus, times 3/5 equals negative 6/5. So that would be one of our solutions, apparently. Maybe I'll write that down here. So negative 6/5, comma, 3/5. And then to get x minus, this comes from plugging in y minus. So negative 2 times negative 1 is 2. So we also have 2, negative 1, apparently, as a solution. Some kind of strange answers this time. I'll go ahead and check them numerically. So what I'm doing right now, you guys, just so you can follow along, I don't know if I can get it all on the screen, but I'm going to be taking both of these. Here's my xy, here's xy, and I'm plugging those back in to this original. So the first point was negative 6/5, 3/5. So here's negative 6/5 plus 2 times 3/5, right? That's plugging into the first one here. And I'm hoping to get a 0 out of that, and I do. then to try negative 6/5 and 3/5 in the second one. Now the y was 3/5. And here we're hoping for a 5, this 5. Good. So that's a good sign. So I'm happy with these. I'm not even going to check the 2, -1. And then also graph to check your answer. So this would just be another way of checking. It's not a great way to produce your answer to graph because your graph won't be perfect, but it's a good way of kind of getting a sense for the sanity of your solution. So what I'll do is I'll graph this line, and then I'll graph what appears to be a circle. So in slope-intercept form, I would want to subtract over the x. So we'll have 2y equals -x, right? Subtracting over that x. Divide by the 2. So y equals -1/2 x is this first one in slope-intercept form, right? We have a +0. So we start at 0. We go down 1 over 2. Down 1 over 2. And I'll make this line. And this other one was a circle, it looks like, right? Centered at 1, 1. Here's the center. And we have a radius of √5, right? The radius would be the square root of 5, not 5. And that's about 2 1/4. So here's about 2 1/4, 2 1/4, 2 1/4, 2 1/4. So there's that circle. We could try to make sense of our solutions now. So the 2, -1, 2, -1, there that one would be, right? So for this one, we're getting a sense for that solution right there. The -6/5, that's a little bit more negative than 1. And then 3/5 is a little bit below 1. So that's this intersection right there. Right, so that's this one. So this is looking like another good verification of this solution. All right. Let's see. So I'll do a couple more. Here's one that says use the substitution method. Sorry, the addition method. So switching methods. So solve using the addition method, also graph to check your answer. So the addition method is that one where we're adding them together, hoping to get an elimination. So we would want to have opposites, right? So when we add these, we want like -3 and +3, or -12 and +12, something like that. So with this one, we need to adjust. So I'll focus on eliminating the x's first. So what I'll do is I'll turn this one into a -12, and I'll turn this one into a +12. So -4. I'll multiply everything here. And then to get my +12, I'll multiply everything by +3. So let's see what these kind of transform into. We have -12 x squared minus 8 y squared And then 35 times negative 4, I believe that's negative 140, but I just woke up, so let me type this in. Yeah, negative 140. And then this one over here, 12x squared plus 9y squared equals 48 times 3, 144. So here's our similar system, and now we actually do have these opposites, so we can add now and things will cancel. So these specifically would go away. We are left with just y squared equals 4. Right, that's pretty nice. Take a square root, plus and minus. So we get y plus equals 2. We get y minus equals negative 2, right? Just to keep track of them again. So that was the addition method. What you can now do is plug these back in. But what I'll choose to do, well, I'll go ahead and actually plug them back in. I was going to use the addition method again, but let's just substitute them now at this point. So what I'll do is plug this back in here and then solve for x. So this first one will be solving for x plus. So we'll have 3x squared plus 2 times, I'll plug in the positive 2. This is 2 squared, and this should all equal 35. So I plugged in y plus, which is positive 2, into the first equation. Now I can solve for x. So 3x squared, this is 4 times 2, this is plus 8, equals 35. Subtract, divide by 3 eventually, all that good stuff. So 3x squared equals 27. Divide by 3. We get x squared equals 9. Okay. So take a square root, plus and minus. So we get that x is plus and minus 3 actually. So from just plugging in the 1, positive 2, I got 2 x's. So this just implied a couple solutions. So we have 3, positive 3, right, corresponds to positive 2. And also negative 3 for x corresponds to positive 2. But what if we plug in negative 2? Right, we still need to plug in negative 2 because it likely corresponds to a couple x's. So plugging in negative 2 now, same as what I did here, just with negative 2. So imagine I did that. Imagine there's a negative right here. Right? When there's a negative right there from plugging in y minus, everything's the same, right? The negative 2 just gets squared now instead of the positive 2, but negative 2 all squared is the same as positive 2 all squared. So everything occurs the same, and we get another plus and minus 3. So we also have these as solutions. So we actually have 4 solutions in this case. If you graph this in Desmos, I believe what you'll see is like a couple of ellipses. And they might not look exactly like this. But you'll get the drift here. So you're finding these 4, 1, 2, 3, 4. And they are somewhat symmetrical. Okay, so I encourage you, if you have time, go ahead and throw these into Desmos. And you'll see these as the intersections. I'm leaving example 5 open, but use substitution, don't use addition, okay? So don't use addition. Use substitution instead on this one. Let's do one more. I do have a bunch of group work ones that I'm going to leave open also, but I'll post the solutions to these. But let's do this one. This will be the last one of this video. It says, find the length and width of a rectangle whose perimeter is 44.8 feet and whose area is 108.63 square feet. So we have a rectangle. I'm just going to draw a quick picture since it was mentioned a rectangle. We're looking for the length and the width. So I'll go ahead and just label those accordingly. For rectangles, just naturally, if you have L over here, you'll also have L over there. And if you have W over here, you naturally have W over there. And the perimeter of such a rectangle would be L plus W plus L plus W, right? Just adding up all the lengths going around. Combining like terms though, you can say 2L plus 2W. And that's the perimeter formula for a rectangle. The area formula, right? It's mentioned, something about area is mentioned, so we may need to know that. This would be length times width. Okay. So we have some information. We know that we want the perimeter to be 44.8. So I'll say 44.8 needs to be equal to 2L plus 2W. Sorry, you couldn't see that. So what I did was I just wrote down 44.8 and set that equal to the perimeter, since the statement is that that needs to be the perimeter. The area needs to be 108.63. So I'll have 108.63 equals length times width. And this is the system that is implied by this information. And this is the system that we need to solve for L and W. I'm going to use substitution. So if I divide by L, then this one becomes 108.63 over L equals W. And what I'll do is go ahead and replace W with this. So 44.8 equals 2L plus 2 times 108.63 over L. Solving this for L. All right, I'll go ahead and simplify a bit. So 44.8 equals 2L plus, and I'll go ahead and actually figure out what 2 times 108.63 is. So that is 217.26, and I still have L on bottom, right, this one. I'm going to choose to multiply everything by L to get rid of that fraction. Okay, so 44.8 L equals, and then distributing this L, we have 2L squared, and then these L's cancel. So plus 217.26. And it looks like I have a quadratic in the variable L. I'm going to go ahead and subtract 44.8 L. So 0 equals 2L squared minus 44.8 L plus 217.26. So I can now solve for the length with the quadratic formula with A equals 2, B equals negative 44.8, C equals 217.26. So L equals the opposite of B, plus and minus the square root of B squared minus 4 times 2 times 217.26 all over 2 times 2. So I'm going to go ahead and throw that into the calculator now. So apparently here's the length. So L equals 15.3 and the length unit was feet, so this would be feet. And then once we know that, I can plug L right here and that'll quickly tell me W. Maybe I'll just keep that here for a second. So 108.63 over 15.3 equals W. .1. So the width would equal 7.1 feet. And you can check this, right? The area must be 108.63. So if I multiply these two together, I had better get that, right? Because that's the area formula. There it is. All right. Have a good one. Talk to you next time.